Coming to the convection, in unit 3, we have basically convection. This is all about convection. We have already seen the basic introduction to convection, but I would like to repeat it once again. Okay, convection is basically fluid flow heat transfer. Convection means there should be a fluid flow. Okay, so that's why it is called as fluid flow heat transfer. Okay, higher the fluid flow, higher the heat transfer by convection. Okay, so what is the law governing convection? Somebody say it. What is the law governing convection? See, this can be a simple question that can be asked for 2 marks, even from the first unit or from the third unit also. So, law governing convection.
Newton law of cooling.
Newton's law of cooling. Good. It is Newton's law of cooling. So, what is the mathematical expression for this one? What is the mathematical expression for Newton's law of cooling? Somebody say it.
HA into T infinite minus TS minus T infinite.
Q is equal to H into A into T minus T infinity. This is a heat transfer by convection mathematical expression, where Q convection is heat transfer by convection measured in watts. What is H here? It is heat transfer coefficient measured in watt per square Kelvin. Okay, this is capital K. What is A here? Somebody tell me what is A here? Area means what here? In this, yes.
Area
Somebody tell me.
direction of heat flow.
Area with which perpendicular.
Area, it's not a perpendicular
With which
area.
fluid is
Area
interacting.
with which fluid is interacting. Okay. It is perpendicular area in conduction case. Area here is area with which the fluid is interacting. Okay. It is measured in meters square. And what is the temperature T? Temperature is the temperature of a solid body. Okay, so you can say temperature of body in simple sense. Okay, it is measured in Kelvin or degree centigrade. Both the things you can measure. And in infinity, what it is? Temperature of what? This temperature
Fluid.
of ambient or atmosphere. Whenever I write infinity here, what is the meaning of it? I'm referring to the surrounding temperature or the atmosphere temperature. It can also be measured in Kelvin or degree centigrade. See, sometimes this watt per meter square Kelvin H value is given in watt per meter square degree centigrade also. Both are equal. Don't confuse if somebody is giving you this degree centigrade here. Okay, this degree centigrade, let us say if the value is given as 10 watt per meter square, degree centigrade is given in question. Then you have to write it as 10 watt per meter Kelvin. Okay, both are equal. I'm repeating once again, most of the time students get confused when it is given as degree centigrade in the question. Okay, there is no need for any confusion. Both are equal because this degree centigrade is taken up here because what we are interested here is T minus T infinity. T minus T infinity means degree centigrade minus degree centigrade will give you some value. Kelvin minus Kelvin also will give you the same value because if you convert it here in the conversion, what you will use, you will have plus 273 here and minus 273 here. Both will get cancelled. That's why both values are same. This is equal to this. That's why watt per meter square Kelvin is also equal to watt per meter square degree centigrade. Most of the times I see students confusing for this. If degree centigrade is given, they use Kelvin plus 273, they confuse a lot and unnecessary things they will do in the exam. No need to confuse, both are equal. Both are equal. Kindly keep this in mind. Right. See, coming to the convection will happen everywhere. Okay, wherever there is a fluid flow, there is a convection happening. Okay, let us say you are drinking water, there is a fluid flowing, and convection will happen. Okay, let us say you have an aeroplane moving in the air is interacting with the aeroplane, you will have convection happening there. So, like that, I can tell you so many examples wherein convection will be happening. But convection is basically of two types. Convection is basically of two types. So first one is forced convection, and the second one is natural convection. Okay, this natural convection also called as free convection. What is the difference between these two? So what is the forced convection and what is the free convection or the natural convection? See, in forced convection, what you do is you will make use of an external device to make the fluid flow, to make the fluid flow. How the fluid flows here? It flows because of some external device or external force. Whereas when it comes to the natural convection, it is because of the natural forces. Natural forces will make the fluid flow. Okay, how the natural forces will make the fluid flow? You know what is called as a buoyancy concept. Okay, this is nothing but buoyancy, Buoyancy, buoyancy. Okay, what is buoyancy force? Okay, let us say you are having a uh, hot body here. Okay, let us say it is at 100 degrees centigrade, maybe something like a plate or something. Then whatever the air that is there above this, air that is there above this, will slowly receive this heat. When this heat is received by this particular air, which is having higher density previously, is staying very near to this body. Now it got high temperature. Because of the high temperature, its density will decrease. Since its density has decreased, it will try to move in the upward direction. Okay, so this is a less, sorry, this is a less density area and this is a more density area. So if the density is lessened, it will try to move in the upward direction. Now, if the density has decreased, as it goes up, the density will obviously decrease. Okay, then the air will try to move in the downward direction. So this movement is nothing but your buoyancy. This is called as buoyancy effect. You are not actually uh, using some external force to make this air flow. This fluid flow is natural. Natural fluid flow is happening, that you call it as a no natural convection. So that's all about the natural convection. Coming to the forced convection, in forced convection you will make use of some external device. Okay, it can be a fan or blower or pressure. Pressure means you will make the water flow in your taps that you use in your home and everywhere. They are moving because of pressure. You have kept them at so and so height. Because of that, so much of pressure head is created. That's why water is flowing. It is not flowing natural kind of thing. There is a pressure created and it is flowing. So it will be coming under the uh, forced convection. Okay, again in forced convection, you have two types. Okay, forced convection is basically two types. One is internal flow, and the second one is external flow. One is internal flow, the second one is external flow. Say in internal flow, fluid will be flowing inside a duct. Duct means it's a tube kind of thing or pipe or something like that. Okay. Here, fluid will be flowing over a body. Okay. The body can be a slab, it can be cylinder, it can be sphere, it can be a bank of tubes, it can be anything. Okay. It is over a body if the fluid is flowing, then we call it as external flow. Let us say here. Okay, this is cylinder here, and for the cylinder, a fluid is flowing like this. Okay, this we call it as an external flow. But when it comes to the internal flows, you have a tube here, and in this tube, fluid is flowing inside. What happened? The fluid is flowing inside. Okay, it is flowing from this end to this end, like this. So this is called as internal flow. That is called as external flow. Right. All right. So when it comes to the internal flow or external flow, you must be knowing something called as non-dimensionalization. In respect to the convection, non-dimensionalization is very important concept. Non-dimensionalization. That is, you will not have any unit for this particular expressions. Okay, they are especially Reynolds number. You have to learn what is the Nusselt number. You have to learn, and you also should learn what is Prandtl number. Okay, these are the very important numbers: Reynolds number, Nusselt number, and Prandtl number that you should learn as far as internal flow is concerned or the forced convection is concerned. Coming to the free convection, that is a natural convection, you will have few more non-dimensionalized numbers. Those numbers we will discuss little later. But when it comes to these things, no, you will have to learn them properly. Right. See, when it comes to the Reynolds number, Prandtl number, any non-dimensional number, you remember page number 120 in data book. Okay, this page number should be known to you very clearly. If you have a data book with you, page number 120, now you go to it, look at it, and you will be in position to understand what I'm going to teach to you now. Okay, and in this, let's go to the Reynolds number first. Reynolds number is represented with RE. This Reynolds number you must have already learned in your previous classes, that is the fluid mechanics itself. So somebody tell me what is the definition of Reynolds number? What is the definition of Reynolds number? Somebody tell me.
To know which type of flow.
To know which type of flow.
Laminar,
Correct. Whether it is a
Signifies
laminar
types of flow, sir.
or turbulent. You can say using this. Very good. So this is the use of it or the significance of it. You are telling. That's fine, but that's not what I'm interested in here. I want the definition of what Reynolds number is. Reynolds number means it is basically inertia force by viscous force. Inertia force by viscous force. This is the definition of the Reynolds number. I'll explain this definition. So to understand this, let us look at the formula. Somebody tell me what is the formula for Reynolds number? Express it in basic terms.
VD by mu.
Rho VD by mu or VD by mu. This is in the first expression is in dynamic viscosity terms, and the second expression is in kinematic viscosity terms. Okay, this is in kinematic viscosity terms. This is in dynamic viscosity terms because mu by rho is equal to nu. This is dynamic viscosity. This is kinematic. Fine. So this is the Reynolds number formula. Okay. If you look at the units for this one, the numerator you have meter square per second. Sorry, meter per second is your unit for velocity, and diameter meter, that's why I wrote meter square per second. Anyways, meter square per second in the denominator. Okay, meter square per second, meter square per second will get cancelled and there is no unit. Okay, so simply put, what we are saying is the Reynolds number is a dimensionless velocity. This is very important. Reynolds number is a dimensionless velocity. If you want to express velocity without a unit, without a dimension, you will be making use of the Reynolds number. Okay, Reynolds number is a dimensionless velocity. This must be kept in mind. Same. We also know that the Reynolds number less than 2000, what it signifies? What it signifies?
Laminar.
It signifies a laminar flow. Laminar flow. And RE greater than that, see, you must have learned it like 2000 to 4000 is a transient, and then from 4000 to, you know, 4000
Turbulent.
to above that, you call it as turbulent. That's what you must have learned in your fluid mechanics. But here, simply put, we take it as 2300 here. Okay, we take it as 2300 here, and we take it as 2300 here. And to take the average effect of transient outside, you take it 2300 and call it as turbulent. Greater than this is turbulent flow. Okay, so I'll be showing this in data book in the next class, but for now, you remember till here. Okay, that is 2300 less than is laminar flow, greater than is turbulent flow. Okay, that is a simple thing that we should very clearly remind. One more important thing is, what is this 2300? This 2300 is called as critical Reynolds number. This is critical Reynolds number. So why you call it as critical Reynolds number? Because based on this number, your flow is decided, kind of flow, whether it is a laminar or turbulent is decided. Okay, right. We have just said that the Reynolds number is ratio of the inertia to the viscous. Inertia to the viscous force. See, viscous forces are more. If uh, viscous force is more and inertia force is very less, then what happens? The flow will be very slow. Okay. See, you take an example of the grease. Grease has very high viscosity and viscous force is very high. Viscous force more and inertia force less. Then inertia forces will be very less for this grease. So the flow will be very slow, giving you a laminar flow. Okay. If the inertia force is very much high, and the viscous force is very much less, then the flow will be very fast. Okay, so this will be called as turbulent flow. You can take the example of water for this. You can take the example of any other less viscosity liquid that is flowing. Okay, in a given, it also depends on the diameter of the tube also. Okay, that's what is seen in the formula, that is Vd by nu. Okay, it depends on the diameter also. Based on the diameter, we actually decide it. Fine. So that's the Reynolds number story. Let me quickly move to the next story, that is the Nusselt number story. Nusselt. Nusselt number. Okay. Can somebody look at the data book and tell me what is the formula for Nusselt number, or what is the definition of Nusselt number? Page number 120 you refer to, and you tell me what is the formula for Nusselt number. Can you
HD
say
by
it?
K.
It is HD by K. Simply put, it is the ratio of heat transfer by convection by heat transfer by conduction. See, what is the formula for heat transfer by convection? It is H into A into delta T. So in place of A, what I can write is, I can write mm, pi d kind of pi d into L, I can write into temperature difference, the delta T, by heat transfer by conduction. If you take it, is Ka dt by dx. A means, here you will take it as pi by 4d square, or pi d itself also you can take, into delta T by uh, L you can take. So this pi dl goes, delta T goes. What you have is HL by K. Or based on the significant dimension, you will take this as D also. So you put it as L itself, that will be more comfortable to you. Okay, it can be both HD by K, or it can also be HL by K. See, if I'm writing NUD here, NU subscript D, it is given in data book, that is mean HD by K. NU subscript, if it is given as L, you have to use HL by K. That's the point there. Anyways, so what happened? So that's what Nusselt number is. Okay. What does Nusselt number represent? Nusselt number represents non-dimensional H, that is dimensionless convection heat transfer coefficient. Is Nusselt number. Okay, Nusselt number is nothing but, it's a dimensionless, unitless H. Unitless H. What I told you just now, I told you that Reynolds number is a dimensionless velocity, and this one Nusselt number is a dimensionless H. Okay, that is the uh, H story. Let's move to quickly the story of Prandtl number. Prandtl number. So the Prandtl number story is PR. It is represented with PR, and the PR formula is mu Cp by K. Okay, this can also be written like, see, what you have in the numerator is, it is Cp. Cp means what? It is the ability to store heat. Okay, and K is the ability to conduct heat. So it is giving you the ratio of ability to store heat. So what I can write is heat storage capacity to heat conducting capacity. Okay, this is what you can write. Also, you can write like molecular diffusion by molecular diffusion, whereas in the numerator you will have momentum diffusion, and in the denominator you will have heat diffusion. In terms of diffusion, if you want to express it, this is what you express. And there is another way of writing this Prandtl number. Okay, that is expressing it in terms of alpha also you can do. So how to do that? I'll show you here. Alpha means what? Thermal diffusivity. Okay, what is the formula for thermal diffusivity? It is K by rho Cp. Okay, so here in Prandtl, what I have is K by Cp I have. Okay, so for this one, what I will do is Prandtl. I will write it like mu into 1 by K by Cp. I will write. Also, I will introduce the rho into this one. So for that, what will I get by Cp by K? I will multiply a rho here. So when I multiply that, no, what did I do? Sorry, it should be like K by rho Cp. This rho was not existing in Prandtl, so I will divide it by here also. So that what I get here is mu by rho is nothing but your nu, that is the kinematic viscosity. And in the denominator, you have alpha. So the other way of expressing the Prandtl is nu by alpha. That is the kinematic viscosity by the alpha, what is it? Thermal diffusivity. So you know that the kinematic viscosity unit is meter square per second, and for thermal diffusivity also meter per second. So there is no unit. Okay, likewise, this Nusselt number also I must have told you what is the formula for what is the unit for H. Somebody tell me what is the unit for H? It is watt per meter square Kelvin, and for D it is meter by in the numerator K unit it is watt per meter Kelvin. So this one goes watt per meter Kelvin by watt per meter Kelvin will yield you no unit. So this one is having no unit. So these are all the non-dimensional terms that we must remember while solving for a problem in unit 3. So that's one thing. And there is one more thing that we must understand here. The concept of bulk mean temperature. The concept of the bulk mean temperature. When it comes to the concept of bulk mean temperature, we are speaking especially about the internal flow. When it comes to internal flow, you will make use of this concept very extensively. So a fluid is flowing in a tube like this. It is entering here with a temperature of T1 and it is leaving here with a temperature of T2. Okay, entering with T1 and leaving with T2. And I want to get the average temperature of this fluid. If I want to get the average temperature of this fluid, what I will use is I will make use of this concept of bulk mean temperature. T bulk mean is equal to T1 plus T2 by 2. So simply put, bulk mean temperature, it is the average temperature or the mean temperature of the fluid that is flowing inside a tube, okay, flowing inside a tube. We are interested in internal flow. Internal flow means it is a flow inside a tube. Okay, so let me quickly do a simple problem here. Okay, I will directly give you the uh, values of the problem. Okay, let us say the T in is equal to the T in is equal to uh, let me say 31 degrees centigrade, and T out is equal to 36 degrees centigrade. Once you know T in and T out, you'll be in position to calculate the bulk mean temperature. Once you know the bulk mean temperature, okay, what's the use of it? You have to calculate all properties in internal flow should be taken at bulk mean temperature. It is very important because the statement is very important, friends. All the properties, whatever the property that you are measuring, see, you have to extensively use the data book for this particular purpose. So while you're taking all the properties from the data book, you will have to make use of the bulk mean temperature effectively. Once you make use of the bulk mean temperature effectively, you will be in position to get all the property values in the internal flow problem. So then he'll be giving you the velocity also. The velocity, let me say it is 10 meters per second, and the diameter of the tube is, let me say it is 2 centimeters. So this data is given to you, and he is asking you to find out the H value. How do you calculate this H value? Okay, this seems a bit awkward because what he has given a velocity, he has given a diameter, and everything else seem to doesn't help you because whatever the formula you know is Q is equal to H into A into delta T. This is the formula, and this formula doesn't have any velocity in it. Okay, you can see that there is no velocity in this. Okay, now let me ask you a question here. See, in this particular formula, all the formula, if you see, do you have velocity in it anywhere? No. Okay. No velocity in formula. Okay. But let's look at the reality. If we look at the reality, okay, higher the velocity, higher the heat transfer by convection. Higher the heat transfer by convection. How can I say it? Simple thing is the example of your cup of coffee. What is cup of coffee saying? Okay, if you have a cup of coffee like this and put it on a table, what's happening to this? If you have a fan, it is going to cool very fast. If you don't have fan, it will take a lot of time. So the heat transfer by convection is hugely influenced by the velocity of the fluid. So velocity of fluid is making a big difference in your heat transfer by convection. That's why we call it as a heat transfer of fluid flow or a fluid flow heat transfer. But this expression is not in position, Q is equal to HA delta T is not in position to tell you that velocity is there in this. So is this a correct formula? Yes, it is a correct formula, but this velocity is taken care of in the H itself. Okay, to take care of the H, using various parameters, like it can be a velocity, it can be the Cp, it can be the density, it can be the viscosity, it can be so on. So many properties will influence the H. To take care of that, there will be something called as correlation here. Okay, these correlations are obtained experimentally. Okay, correlation obtained experimentally, and among this correlation, we will be using the Ditters-Boelter correlation. Ditters-Boelter equation or correlation, and it is represented with Nu is equal to 0.023 into Re power 0.8 into Prandtl power 0.8. Can you see the three dimensionless numbers you are using here? Using the dimensionless numbers, you are actually correlating the properties here. Here in this property, you have Hd by K, and in the Reynolds number, you have Vd by nu. In the Prandtl number, you have nu by alpha. So all these properties are correlated using this. So whatever the H effect it is there, it is actually related with the velocity also, and other things like the Cp, all those things are there already inside this alpha. So that's all for today. I'm going to solve this problem in the next class. So this problem will be of great importance for you guys. Come to the next class for sure.